Today we will study magnetic field. What is a magnetic field? Magnetic field is very much like electrical field we have already studied before. Now let's see some of the properties of a magnetic field. Now what happens if you take a charge and let's say this is a magnetic field. If it moves with a velocity v, this charge will experience some force. And what is this force equal to? This force is equal to Q V by U. Where F is the force experienced by the charge, Q is the charge itself, Q is the charge on the particle or whatever, V is the velocity with which it is moving in electrical field B. So this is a vector. It will have its direction as well as magnitude. Okay. Now, if we take a current carrying conductor, let us say we take a current carrying conductor and there is a magnetic field around it, then this conductor will also experience force on account of magnetic field. And how much is this force experienced? The force experienced by the conductor carrying current I is given as I times its length, the length which is immersed in the magnetic field B. Again, since force is a vector, this cross product is also a vector. Then if we take a loop which is carrying current, and if we again suspend it in a magnetic field B, this coil will experience a torque. Torque meaning one side will try to go this way and the other side will try to go this way. It experiences a torque. We will study the reason for this torque later on, but just to give you an idea overall, the torque will be given as I A cross B. Torque is equal to I, the current that is flowing in this loop. A is the area of this loop. If I say that this is bound by A, B, C, D, then A is area bounded by A, B, C, D. This loop into B. B is the magnetic field. Again, this is a cross product because tau is a vector. This again a vector product. Now what is A? A we know is normally a scalar product, but in this case A is a vector product, and the direction of A is, if you have a coil in which you have current flowing through it, what you do is you put a screw perpendicular to the surface of the coil and then rotate it, and then rotate the screw in the direction of the current. For example, in this case, we will be rotating like this. Because the current is flowing like this, we also rotate it like this. Now, if we rotate a screw in this direction, it will advance in the forward direction. So this is our direction of A. B we know is magnetic field, it has its own vector. And since this is a cross product, it is vector product. Sometime we combine this, we call this as this is called magnetic moment. So our tau becomes mu cross B. Okay. Now, this was regarding force that was experienced by a moving charge in a magnetic field or by a current carrying conductor in a magnetic field or by a coil in a magnetic field. They were all basically related to force experienced on charge or the conductor. Now, let us try to calculate the magnetic field due to a current carrying conductor. Okay. Let's take a conductor. Which is carrying current I. Then we want to find out at point P, which makes, let us say, we have a small portion of the wire, which is DL, makes R radial vector to the point P, then the magnetic field at P is defined as mu naught I dl cross R divided by 4 pi R cube. So if we say this as dB, what this equation says is that if we take a small length of conductor dl, then the small magnetic field created by it at point P, which makes a position vector R with this dl, then the magnetic field given by this dB, generated by this dB, is given by this formula, wherein I is the current being carried by the conductor, dl is the length vector of the conductor, R is the position vector. Now, the direction of R is direction of DL is in the direction of current, with one additional point that it is also tangent to the wire at that place. For example, if magnified, if this were the conductor, and if we were to take DL at this point, then we will take a tangent, and then okay. So we yet don't know what is the direction of DL. The direction of DL is given by the direction of current. If this is the direction of current, this will be the direction of DL. Okay. Now, instead of DL, DB was a very small length. If we want to take a longer length, then what we can do is we can integrate. We can use this formula at every point and integrate over DL. So after integrating over DL, we'll get magnetic field due to a length of the wire, which may be in any configuration. Now, it doesn't say that it is not necessary. This formula says that it is not necessary that my DL should be straight, my DL should be long or short. No, it doesn't say anything. It says your current carrying conductor could be of any shape. So long as you are able to do a DL cross R, that's fine. Now, this DL cross R is for small DL. If you do it over a larger length, then you get the magnetic field due to a larger piece of wire. Okay. But what if we take a very long conductor carrying current I, and if there is a point P which is at perpendicular distance D, then do we know what will be the quantity, magnitude of the magnetic field here? We already know the direction of magnetic field will be like this. And the magnitude is given by mu naught I by 2 pi d. Where B is the magnetic field created by a long current carrying conductor, which is carrying current I and which is at a distance D from the conductor. Now let's take the case of two parallel conductors having current I1 and I2 in the same direction. Then what will happen? We know that if we try to calculate magnetic field on this wire, because of this wire, let's designate wire A. This is wire A. This is wire B. then what is the magnetic field on B because of A? Magnetic field is going to be like this. We have seen the B, magnetic field B because of A on B is given as mu naught I 2 pi d. If d is the distance. Okay, and we have also seen if there is a conductor which is carrying current in a magnetic field, it will experience force. We have seen that. And what is this force equal to? This force is equal to current times L cross B. So what will be the force experienced by B, which is equal to I2, the current carried by it, then its length, into the magnetic field which is on account of A, which is mu naught I 2 pi d. And what will be the direction of this force? This force is L cross I. Now, conductor A, the direction of magnetic field will be like this. And if we take at this point, this will be tangential to the circle. So the direction of B will be here. And what is the direction of L? Direction of L is same as direction of I. So what will be L cross B? L cross B will be this way. Okay. So we can say FB is on the left side, directed to left side. Okay. All right. Now, if we do this same treatment on the other conductor, then what happens is, because of I2, because of conductor B, let's draw another diagram. This is A, this is B. Both are in the same direction. I1, I2. This will create a field like this. So if at this point, if we take tangent, this tangent will be coming out like this. This is the direction of our B. And what is direction of L? Direction of L is this. So what is L cross B? L cross B will be going in this direction. So force on A is towards the right side, and the quantity wise it will be the same. So what does it mean? This conductor is being pulled here. This conductor is being pulled here. So they attract each other. If the currents were anti-parallel, one was going like this, one was going like this, then what will happen? On account of this, the force experience on this will be this way. The force experience on this, on account of this, will be this way. So the conductors will repel each other. There is another law called Ampere's circuital law. This law also helps us find magnetic field due to current carrying conductor. First, we will see this law, and then we'll see why do we need this. What are the limitations of Ampere's circuital law over Biot-Sarvart law? Okay. Now, what this law says is you may have number of currents going in and out, or okay. Let's take a surface. Then you have some current going in, I1, I2, some current coming out. What you do is do sum of all the currents. Okay, all right. Then what you do is you build a closed loop around all these current carrying conductors, a closed loop. It doesn't matter what shape it is, absolutely any shape it can be. And if you see, if you take this loop, just for the sake of interest, if you dip it in a soap solution, there will be a small film created on this surface. So this makes our explanation simple. So there will be some current passing from bottom up and some current going from top to bottom. Then what this law says is that there will be magnetic fields which may be same or different at each point. What you do is you take you take a small length of conductor, which is DL, take a dot product with magnetic field at that point, all right, and then do a line integration of this. You integrate this quantity for small dl over this B dot dl, which is going to be a vector, basically a scalar product. You do this integration over all these along the periphery of the loop. Now, if you do that, then this is equal to mu naught I. Okay. V was a vector, dl was a vector, and since this is a dot product, the result will be a scalar product. Okay. Now, just for the sake of interest, if this happens, if this loop were a perfect circle and V was constant all along, then what would have happened? DL would have got integrated into 2 pi r u naught I, and we would have got okay. Now you have to remember very, very carefully that Ampere's law is not applicable when conductors are small. Why is that so? Because if the conductors are small, there is an abrupt change in current, and which will result in abrupt change in magnetic field, which cannot be accounted for. So what do we do in such case? We have a small conductor and we still want to find the magnetic field because of that. What do we do? Simple. You go to Biot-Sarvart law. There is no restriction on the size of the conductor at all. In fact, wherever you can use Ampere law, you can use Biot-Sarvart law very easily. But why don't we do that? We don't do it because, have you seen with what convenience we have got this? If the things were symmetrical, how conveniently we got magnetic field? That is the beauty. Because it is easy to use. This law is easy to use. But at the same time, we have to remember that it is not applicable to small piece of conductors. Now let's try to calculate the magnetic field due to a finite length of wire at a point P. Which is at a distance d. And if we draw this angle becomes theta, this angle becomes theta 2, and the current flowing is I, then B is given as mu naught I I'm not going into the derivation, which you can always work out. So what this says is that if you have a conductor, a finite length of conductor, let us say L, L is the length of the conductor, and you have current I passing through it, then the magnetic field due to this piece of conductor at point P, which is at a perpendicular distance of d, is given by this formula. D is the distance, this distance. Theta 1 is the angle which this line makes with conductor, and so is theta 2. Now suppose we were to see, will this formula yield the same result as earlier? For long conductors? What we've seen is for long conductor, this we saw for long conductors. Okay. Now let's work it out. If this conductor becomes very, very long, then what happens to theta 1? Theta 1 will keep decreasing, and it will go to almost 0. Okay. No, sorry. If the length keeps increasing, theta 1 will keep increasing until it goes to 90 degrees. Okay. Now, sorry, this is not the angle. The theta 2 is not this angle. Theta 2 is this angle. And what happens to theta 2? Theta 2 almost becomes 180 degrees. So what happens to our this expression? This expression becomes small correction. When the length keeps increasing, this theta 1 keeps decreasing and it will go to 0 degrees if it is infinite length. And theta 2 will almost become 180. So what will be our this expression? This expression will be cos 0 is 1 minus cos 180 is minus 1 again. So this becomes I 4 pi d into 2, which is equal to I mu naught I over 2 pi d. This is what we see earlier. Mu naught I over 2 pi d. Through this formula, we have known the magnitude of B. But what is the direction of B? Direction of B is again given by right hand rule, which says if you take your right hand and close the current in your fingers, and if the direction of current is direction of your thumb, then the direction of curling of your fingers will be the direction of B. Okay. There's another electrical device called solenoid. What is a solenoid? Solenoid is basically, if you take a magnetic or non-magnetic core and if you wrap electrical wire over it and pass current through it, then what happens? There is a magnetic field generated inside. Now there are few very subtle characteristics of this field. First of all, the field in a solenoid is constant within the solenoid. Which means it doesn't matter whether you are taking, this is our direction of B. If you take B here, 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 anywhere within this solenoid, the lines will be parallel and they will be constant, uniform. That is rule number one. Second is magnetic field outside solenoid is zero. That means this magnetic field is existing here only. Outside the solenoid, B is zero. These are the two observation or rather conditions with the solenoid. And the magnetic field produced in a solenoid is equal to B is the magnetic field, N is the total number of turns. You may have 1 turn, 2 turns, or whatever number of turns you have. I is the current passing through it. And L is the length of solenoid. You have to be careful over which coils are tightly wrapped. Now, for example, if you take a long core, but if you wrap it only on this area, then we will, this is current out, this is current in, then only this length will be coming to picture, not this whole thing. And we can say N by L is the number of turns per unit length, and if we designate it as N, then our magnetic field inside a solenoid becomes N by simple, because L gets in N, L and N gets absorbed into this expression of N. Okay. We can prove this formula using Ampere's circuit law also. How? Let us say this is the coil coming out of the paper plane. Sure. If we cut the solenoid like this, then we will get the conductors will be exposed. we are coming out of the plane of the paper, and these are the conductors which are going into the plane of the paper. Okay. Now one thing is show that B is constant anywhere inside the within the solenoid. Then what happens is, let us take a small closed surface. Closed loop, not surface, I would say. Because what does Ampere law says that B dot dl integral is equal to mu naught. Says take small portion of length of wire and take a dot product with B. B is constant everywhere. If I designate this as A, B, C, D. Now, if you take this loop A, B, C, D, then if you take this side AD, the line vector is pointing this way and B vector is pointing the dl vector is along the current. So this is the direction of dl vector and this is the direction of B within the solenoid. So both are perpendicular to each other and the dot product will be 0 here. Similar the case with side BC. Again same thing. The vector dl vector is in this direction, but the magnetic field is in this direction, perpendicular to each other. This also goes off. Now what happens to AB? Since AB is outside the solenoid, there is no magnetic field. So this also goes off. The only field which will, the only side which will contribute to magnetic field is dB. And how much is the magnetic field created? If we take integral of B dot dl, B is constant everywhere, dl sums it over to length. So this becomes B1, and which we know is equal to B1. Okay. And let us say if there were n number of coils, then this gets multiplied by n. So our B becomes n mu naught, sorry, n if we write total number of coils, n mu naught I over L. This we call as small n. This is this is how you can prove that magnetic field within a solenoid is given by n, which is the number of turns per unit length, and I is the current flowing through it. This formula does not give you the direction of current. It only gives you the magnitude. How do you find the direction of the current? Again, simple right hand rule. Right hand rule will give you the direction of the magnetic field. Now let's try to find out magnetic field created due to a circular loop. Let us say this is a circular loop of radius A, and there is a point P which is d distance away from it. Then how do we find out the total magnetic field at point P because of whole of this loop? We want to find magnetic field at point P because of whole of this loop through which current I is passing through. So what we will do is we take a small piece of section of this loop here. This is carrying current in this direction. So this DL will create magnetic field here. And what will be the direction? First of all, it will be perpendicular to itself. So we can resolve it into two components. One is along with this, and another is. Similarly, if we take an element just opposite to it, what will happen? This again will have a field perpendicular to it, and so this will have a field. And again, we can resolve it into these two will cancel out each other, while these two components will add up. And if we do this integration, since they are symmetrical, the horizontal component, because of both sections will be same, the vertical components will cancel out each other. And if we integrate the whole thing over the loop, then what we get is, we get an expression V is equal to V naught I square over 2 V square plus D square 3/2. This is the magnitude of magnetic field due to a loop whose radius is A, who's carrying a current of I, and at a point which is at a distance D away from it. Now there can be some special cases of this, that in case our D is far greater than the radius, then what happens is we can ignore the A terms, and what we get is V is equal to mu naught I A square by A we can ignore, this becomes dq. This is when distance between the coil and the point where we want to know the magnetic field is too far compared to the radius of the coil. Now what if we squeeze this D and bring it to the coil itself? Then what will happen? Our V will become not I A square 2 I square plus D square divided by 2. D is become 0. So this becomes mu naught I square over 2 AQ, and this becomes mu naught I. We had stated earlier that if you take a coil carrying current and you suspend it in a magnetic field, it experiences torque. Let's analyze it. Let's take a coil we attach a battery so that current can flow like this. And let us say we designate the coil as Q minus, and we create magnetic field. You can create it by any means. Just for the sake of example, we put two permanent magnets and we put magnetic field like this. Now, can we calculate the force acting on each side of this loop? Yes, we can. How? Force acting on a current carrying conductor, we have already seen, is equal to I L cross V. Here I is this is the force on the conductor carrying current I, whose length is L, and it is in a magnetic field B. Okay. So then, what is the field force on segment PS? Now, if we try to find out the force acting on side PS, what it is? This is PS, this is the direction of current, and this is the direction of B. Direction of current and DL is the same. So, the force on PS will be I length. Let us say this is width is A, and this loop has width of A and length of B. Then the force on side PS is equal to I times length, length is B, to field B. Similar will be the case with QR. So on PS we have IBS, on QR we have IBS. Now what happens on SR? In case of SR, our direction of current is this way and our B is also this way. So the cross product will be 0. So contribution of SR as well as PQ are 0. So the total torque will be what if this is, let us say, forces were perpendicular to the arm, then this force and this force is same, and this makes a couple with half distance as a by 2. And if we add both the couples, then what we get is this is our torque because of both the sides. Now this was the case when these forces were perpendicular to the arm, but if it is not so, then what we will get a sine theta in between as well, which is the angle between this arm and the magnetic field. Now if we take, this can also be written as I. A and B is the area. B is the magnetic field. Okay. So this is our torque, and we have special designation of this, which is M. So our torque, if we write in vector form, is the direction of M is same as direction of A, area vector. And what is the direction of area vector? If this is our loop, what we do is we put a screw perpendicular to the plane, because the vector is going to be perpendicular to A as well as B, and then we rotate the screw. We take the screw perpendicular to the plane and we rotate the screw in the direction of current. This is the direction of current, and in this case it will go inside the paper, so it will advance in this direction. So this will be the direction of our area vector. Our next topic is moving coil galvanometer. A moving coil galvanometer is a very simple device. What it has is, there are two magnets like this. They are specially shaped. And there is a coil in between. One side A, and we have coils wind around it. Now, there is a scale, and a pointer is attached. This is the scale. Now what happens is, when current I is passed through the galvanometer deflects. because the coil experiences some torque, and the torque is proportional to the deflection. Let's see how. The torque that the coil experiences is given by force A sin theta. This force is the force on the arm of the coil, which basically is making the couple. Force is, as we saw before, this is force, which we calculated earlier. A is this length, and sin theta, now instead of showing like this, what we'll do is, let us say the coil turns slightly. This is still F, this is still F, this is A by 2, this is A by 2, and this is a area vector, direction of area vectors. Area vector is perpendicular to the coil, and this is our direction of B. And this theta is the angle between area vector and magnetic field. So in general, if the coil is tilted so as to make this theta, then torque will be so much. Now, as we mentioned again earlier, this galvanometer has a very special magnet which produce radial magnetic field. What does it mean? It means that magnetic field is always parallel to coil. Meaning thereby, if let us say suppose this is the position of the coil, the magnetic field will also be like this, parallel to it, because of the special construction of the, this is the coil, magnetic will be like this. If if the coil happens to tilt only this much, then magnetic field will be like this. And if it, let us say, coil becomes like this, then magnetic field will be like this. This is called radial magnetic field. In this case, this theta is always 90 degrees. So theta is 90 degrees always, which means that our tau is f time only this much, because sin theta is 90 degrees. Sin 90 is 1. If you substitute the value of f, it is I B U A, where L is the length of the coil. This is the width of the coil. So our tau LA is equal to k theta if the coil tilts by rotates by angle theta, then this is the torsional constant of the spring. This is the torque produced, anti-torque produced by the spring, and this is the torque produced by the magnetic field. So in such case, our theta becomes and if we combine length and A, this becomes area of the coil. Now this is for one coil, and if you have a number of coils, then this formula becomes I. This is the generic formula. Now what is the current sensitivity? Current sensitivity is how much does the coil turn for a given I. Theta we have already calculated earlier, and I becomes equal to K also. Now to convert a galvanometer into a voltmeter, what we do is we take this galvanometer and attach a very high resistance in series. So the voltage sensitivity is defined as deflection in the galvanometer per unit voltage. Theta we have already seen is equal to and B is total voltage. The total voltage is more or less completely dropping over point A and B. So the voltage drop across, if this is the current, and the voltage drop across A and B is This is the resistance which we put in series with the galvanometer to convert it into a voltmeter.